Okay, in this video, I'm going to be going through the SST electronics paper from 2021. But before I start, right, I'm just going to say a few things. Firstly, this paper is hella out of syllabus. Although it is, I still strongly recommend for you to try at it. Okay, wait, hold on. I'm seeing this here. Is this edited in? Okay, and the answers. This paper has been tried by one of my students, if I should say. So it does appear that the questions that were out of syllabus has been the marks have been removed. So I don't know. I mean, I really don't know. I just got back home, and then this is the first thing that I'm doing for some reason. Okay, let's just go through it. So, oh, it wasn't. Oh, okay. So this is not. This was just here. Okay, you know what? Let's just start. Okay, so before I begin, I highly recommend you try it first. Okay, and then blah blah blah. So let's just go. Okay, first question. Pulse width modulation can be used to transmit data. Really? Okay, 1.1 shows how X is modulated with a carrier signal. Yeah, this is our syllabus. Oh my gosh. This is so out of syllabus. Okay, my bad. This is also out of syllabus. Okay, but anyway, state the type of signal shown in 1.1. X is analog. Okay, I guess that makes sense. Z is digital. Yeah, I guess that should be. Yep, nice. So you get this. State the difference between Y and Z. Carrier signal Y is periodic, while carrier signal Z is non-periodic signal. Is that how you spell signal? It is. Wait, why does it look weird to me? Okay, I don't know. Oh wait, this is 2 marks. Oh my bad. Okay, yeah. So you get full for here. 2.1 shows a common emitter amplifier that is commonly used to amplify signal from sources such as microphone or photodiode sensor. Okay. Deduce the output KVL equation. The output KVL equation. Output is like here. What the heck is this English, bro? That's so unclear. I mean, yeah, it could be. Okay, what I'm thinking, right, is it's either like the KVL is from here or like here. Okay, it's probably this side. But honestly, for this one, I have no freaking clue. What? Let me just see. VCC minus ICRC, which is just V of C. Oh, so it's here. Okay, wait, hold on. Minus VCE minus VE is 0. Accept other possible manipulated answers. So this is the answer. That's so stupid. Who said this paper? Oh crap. Okay, let me explain what is going on here, okay? So look at this transistor, right? You can actually split it up into two simpler circuits, right? So we have the transistor. Okay, it's not like a lot of drawing space. We have the transistor here, right? And then note how there's like this entering here and then this exiting here, like this, right? So what we're doing is we're just looking at it as one line, and then we're gonna note, oh, there's a resistor here. Oh, there's a resistor here. Oh, there's VE. Oh, VC. Oh, VCE. Oh. And then what we're gonna do is we know KVL is equals to like 9 volts, which is the source, based off KVL, 9 volts, which is the source here, is equals to the voltage of everything added up here. So then that will be equals to the voltage across the resistor C, the voltage from C to E, and the voltage of the E resistor, and then that's basically this. That's basically this. It's just that they shifted everything to this side, and instead of 9 volts, they said VCC, which is stupid because there's already 9 volts. But all in all, this is a very stupid question, lah. And it's probably it would work with this loop here, this line here rather, because again, if we try to simplify, right, we actually get this. We have a resistor here, and then we have like kind of a capacitor here, and then from 9 volts, but it's kind of more complicated. And we don't, yeah, okay, yeah, it can't be this, because V in is a bit off already at this point. So I mean, yeah, again, this is our syllabus, but it's just that is this, when they asked for KVL, you try to find where is it, right, that there's a complete circuit. It's here lah. It's here. And then can you deduce from this complete circuit components that actually take up voltage? You can. Then you know KVL, because all these three voltages add up together will be equal to the source. And then you can form your equation already. Okay, let's just move on. Calculate VC if IE is 1.5 milliamps. Calculate VC. Oh, okay. Oh, this is just V equals IR lah. So we want the voltage, and what we need is current times resistance. We know current because E here, 1.5 milliamps, and then times the resistance 1.0 kilo ohms. Convert the prefix and then do the math, and then you should get the answer lah, which is oh, they did it. They did it like that. They're using KVL, but they also did 1.5 milliamps times 3K. What is 3K? Oh, VC! Oh, this! Oh, crap. Oh, y'all didn't see that. Oh, my bad. Okay. My bad. Huh. So, sorry. VC would be equals to IE times RC. So, again, it's KCL. Okay, KCL states, not KCL, okay, just the general rule is that current at any point in a series circuit is equal. So they're telling us that IE, which is here, this is the emitter of the BJT, it's telling us that there it is 1.5 milliamps, but this is a series circuit, so we also know that 1.5 milliamps is here as well, and then this relates to this resistor, and then we already know, let's put in the values. So okay, wrong. Determine the base current IB, 0 amps. There's no way that's right. What? 0 amps? Why? Base is this 0 amps. IB, oh. Approximately 0. Is it if you use the voltage divider, you get approximately 0? Okay, I wanna try it, bro. What the heck? Okay, so what is going on, man? I don't think it's true. What? This doesn't give about 0. 82. Yes. It doesn't have 2.58. Why is it 0? I have no idea. Okay, I'm just about this right for now. Determine the gain of the amplifier. Oh, okay. Okay, you wrote current gain is equals to IC over IB, and then you didn't do anything. Okay, so you just need to find IC and IB. So you know IC, IC is 1.5, and you know that because of IE is 1.5, and then oh, that's not right though. Wait a second. Oh, okay. So no, basically what I'm thinking, okay, IE is equals to IC plus IB. Based on the answer key, IC is around 1.5 milliamps as well, since the answer key says that IB is 0 amps, or around 0 amps. So now you're dividing by 0. What's the answer key say? This is voltage current gain. It's just voltage gain, it's not current gain. Yeah, I'm skipping this. We don't even learn this, so there's no point. Or we don't really. Yes. Okay, so let's just move on. Part D, figure 2.2 shows the output waveform measured across V out. Oh yeah, just to let you guys know, this is using a BJT transistor, right, to amplify AC signals, which we don't really touch that much. So I guess this part isn't really useful to us, but I'm still going to go through it anyway. So yes, figure 2.2 shows the output waveform measured across V out. Draw the input waveform on 2.2. Did you draw this? Wow, it looks pretty good. So, and label the value of peak. Oh, this is V out. Oh, okay. Oh, you just didn't do it. You just didn't do it. Also, 0. Okay. Okay, so the voltage gain is 3. 3 is 3. For these kind of amplifiers, the output will remain in phase of the input. Or the input, yeah, okay, what I said. So, I'm not gonna explain this. It's not worth it. Let's just move on. Okay, IV graph of three three different components. State and explain which conductors are state and explain. Okay, non-ohmic. B and C are non-ohmic. Why? This is because a non-ohmic conductor will not have. This is because a non-ohmic conductor will not have a constant increase in the resistance. That's not true. While B is increasing rapidly and C is 0 before having a sharp increase. That's a terrible explanation. Terrible explanation. The first statement, this is because a non-ohmic conductor will not have a constant increase in the resistance. Component A has a constant increase in the resistance, right? Oh wait, it doesn't. So I'm stupid. Resistance is constant, cause okay, this is a VI graph, right? Resistance is V over I. To get resistance here, can we take the gradient? No, we can't. We'll get IV. Why am I thinking so deep into this? Give me a second. B and C are not. Okay, you get 1 point for now. I is not directly proportional to V. That's it. Yeah, that's all you have to say. It's direct proportionality. I don't think I. No, yeah. Direct proportionality highlighted in red is a keyword and you don't have it. So, sorry. Component A is a 1.8 meter long. My bad. 1.8 meter long and has total resistance of 0.046 ohms. and then some info about it. Calculate the resistivity of component A. Yep, resistance is equals to resistivity times length divided by cross-sectional area. So, geez, the handwriting. So if you put it in correctly, then you should have gotten the answer, which you have, so 1 mark. Hence, determine the material that is used to make component A. Oh yeah, we just go back. The resistance, okay. The resistivity is 2.81 times 10 to the power of negative 8 ohm meters, which aligns with this. So yeah, aluminium. Component X has a resistance of that. Component Y has the same cross-sectional area and resistivity as component X, but twice its length. Determine the resistance. Yeah, it should be just times 2. Yep. Yep. Okay, combinational logic circuit. I like the labeling. This is good for circuit analysis if you're not really familiar with the logic gates. 4.2 shows a timing diagram. Complete the timing diagram of the circuit. What? Why are they asking us to do so stupid things, bro? Okay. Okay, they gave us A and B. D, E, F. Okay, so the conditions. Okay, I'm just gonna go at it. Okay, how do you even start a question like this, right? We're looking at the outputs of D, E, and F. So just focus on one. Okay, this is pretty obvious advice, but advice is advice. Focus on one. Focus on the inputs. They already gave us the inputs A and B for this D, right? So, and then we have a NAND gate. So we just need to know which conditions does the inputs of the NAND gate have to be to get 1, and we can use this. We can get that using a truth table, which this guy has written here. So nice. Then we just use that, and then we check. Oh, okay. In this instance of time, oh, what is A and B? Oh, 0 and 1. Oh, what does it mean here? 0 and 1. Oh, 1, 1, 1. Oh, put it here like that. That's it. And you do that for the rest. And then you do that for E at least. F may be a bit difficult because you're dealing with 3 inputs. You're dealing with C, you're dealing with E, you're dealing with D. So for this, you might not be able to use a truth table. You might have to understand how a 3 input AND gate works. And for that, it's very simple. As long as all inputs are 1, then the output is 1. Otherwise, it won't have. And then you just go about it again, slowly, grueling. It's a grueling system, but it is a foolproof system. And then if you do it right, you'll get it all right. Which Ryan, oh crap, I name dropped. Yeah, which this guy, yes, he got it all right. Oh, okay, here, my bad. So yeah, good. Write the Boolean expression for D, E, and F. So D, E, and F. D and E is just writing the Boolean expression for the NAND gate and the NOR gate. Okay, just don't write X equals, because expression X equals something is an equation. Expression is just like this. Am I about to get embarrassed? No. So yeah, this is for NAND gate. This is for NOR gate. X equals A plus B. Okay, or A plus B. Is this right? Huh, no. Except this, or, oh, it's an OR gate. Oh, my bad, guys. So okay, yeah, the conditions for an OR gate is, or a triple input OR gate is, at least one of the inputs has to be 1. So, oh, this is very simple lah. So then it will just be this plus this. But apparently they accept D plus E plus C. I disagree. Don't do this in your O levels. I disagree. Don't do it. It is not worth the risk. So it'll be this plus C. Because that's what we're ORing here. We're ORing D, E, and C, but we know D, we know E. Yes. So that's it lah. But in the answer key, they actually say, oh no, yeah, nothing. Yeah. So you get 2, because this is just wrong. Okay, universal gates can be used to represent any other logic gates. That's correct. My bad. Draw in the space below to show how a 2-input OR gate can be represented by universal gates. I think you just didn't do it. Okay, I'm gonna do. Okay, basically, right, there are 2 universal gates. If you want to know more about universal gates, you can watch my video. There's the NAND gate and there is the NOR gate. Okay. To make an OR gate, okay, for the NAND, or when using NAND, it's quite difficult. You have to do this. This is for NAND. I'm not going to explain why this works. I have a full explanation for that in my video on universal gates. Okay, where AB is the input, X is the output. For NOR, sorry, it's actually much simpler. It's just this. Hold on. Am I going insane? No. Okay. It's like this. Okay. Just note, right, that these bits here, these are inverters. Okay. And that's all I'm going to say. Am I right or am I right? Whoa, I'm right. Okay, let's move on. So yeah, 0. Okay, figure 5.1 shows an astable multi-vibrator. Really? Okay. Determine the frequency at which LED 1 vibrates, which is the output. Oh, so we can just use... Oh, astable, yeah. Yeah, we can just use this equation, which finds the period at which the output frequency is. Oh, no, which finds the period of the output frequency. So period is the length of time between each waveform. So this would be 1 period. Okay, and then using this equation, we can find it. So you just need sub in values. And then we can find the period, which in this case is 4.58 seconds. And then we know frequency is equals to 1 divided by period. So you just plug it in, and then you should get the answer lah. And if you've done it right, which you have, then you'll be right. Oh, really? Explain why it is impossible for the circuit in 5.1 to achieve 50% duty cycle. As the astable multi-vibrator has a frequency of 0.218 Hz, LED 1 would be flashing on and off very quickly. This means that T on is very low, and it will not be at least half of the total time of 4.85 seconds. Hence, it will be impossible. No, that's just wrong. That's just totally wrong. The capacitor charges through R1 and R2, but only discharges through R2. Hey, it's not wrong. It's not wrong. It's not wrong. Hence, the charging time will always be larger than the discharging time. Oh, huh. Okay. It will never be 50% duty cycle, or the T on will always be lesser than the T off and never equal. Okay, that's not right. It will always be lesser. The reason is because when charging, when the capacitor is charging, right, you have to go through 1, 2 resistors. When the capacitor is discharging, it only has to go through 1. You see, like this discharge, inside the chip, it will complete a circuit to allow this capacitor to discharge. And since when it charges, it has to go through 2, but when it discharges, it has to go through 1 only, it takes a longer time to discharge. It takes a longer time to charge up because it experiences more resistance when charging rather than as compared to when discharging. And as such, T on will always be lesser, and that's the reason. Okay, I think this is my bad. I've never went through this. So yes, a diode is added in parallel to R2. Explain why, with the addition of this diode, it is now possible to achieve a 50% duty cycle. It becomes a monostable multivibrator, as current will flow through D1 instead of R2. Hence, by using the formula T equals 1.1 RC, the frequency would be possible to achieve 50% duty cycle if the T on is long enough. What? What? No, 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 no. No, bro. Wait, did I mark this right? Yo, my bad. This is wrong. This is wrong as well. No, it does not change to monostable. The configuration is threshold and trigger connected together, bro. Dude, what? No, man. No, it does not change, bro. What? The capacitor will only charge through R1 and only discharge through R2. Since both R1 and R2 are the same, 50% duty cycle will be achieved. Okay, how this works is this. Okay, when the capacitor is charging, current will flow from here, and then now, right, the current, you see there's a junction here. Ignore discharge, right? It won't go here, lah. Okay, just accept it as it is. We don't have to care about it at your level. Whew, tough. So it can either go through the LED or the resistor. What do we know? We know that electricity follows the path of least resistance, and in this case, the resistance of the LED is significantly smaller than the resistance of R2. So it won't even bother going to R2. It will immediately go through this diode and then charge the capacitor. And as such, during charging of the capacitor, it only goes through one resistor. And the resistance of the LED in this case is negligible. And then when discharging, okay, the current will flow through this resistor and then discharge. And it cannot go up here to go through this. Why? Because the diode prevents backflow of current. So when charging, when discharging, current flows through one resistor only. Yes, and in charging and in discharging, the resistance of the resistor is the same, 10 kilo ohms, 10 kilo ohms. And that's the reason. Okay? Alright. Table 6.1 shows numbers in a range of number systems. Complete the table by adding the missing numbers. I ain't going through this, bro. I'm just gonna mark if you're right. You can watch my video on binary if you don't know what the hell is going on here. What? Oh. Bro, what is this? Did someone copy this over? This answer key sucks, bro. The paper sucks, bro. Circle the largest decimal value for a 4-bit binary system. Yeah, 15 is the largest. Give one example of a number in 4-bit binary that cannot be converted to BCD. Except any of these. Yeah. Alright. 7.1 shows a circuit used to detect AC signals. Okay. This is a voltage comparator. I think so. Yeah. Name the component IC1. Okay. Are they... No way they're asking for that. What is the standard of electronics in this school? I mean... Okay. Okay, I'm gonna mark you right. Okay. I don't think in the O levels they're gonna ask you the actual IC like code. Alright, anyway. The reference voltage at pin 3 is set to 4.7 volts. That's true. Why am I saying that? An input waveform Vs is applied at pin 2. Draw and label the voltage signal at pin 7 on 7.2. Yeah, this doesn't seem wrong, so I think this is right, yeah. Nice. It's like 3 marks. Yeah. So, do I want to explain this? Sure. So, basically, right, as we know, the voltage comparator, what it does is, if the voltage at the positive is higher than the negative, then the output will be 1 or 8 volts. If the voltage of positive is lesser than the negative, then it will be 0 or 0 volts. Okay, keep that in mind. Now, this will be our input voltage, and as long and 4.7, they tell us in that question that the negative, right, the voltage at the negative pin is 4.7 volts. Okay, so we mark 4.7, and at any point of time, if the input voltage is higher than 4.7, then at that point of time, the output will be 1, logic 1 or 8 volts. If not, it will be logic 0 or 0 volts. That's the explanation. That's it. You want a more in-depth explanation of voltage comparators? I have a video, of course. Yeah, I always have a video. Explain how the component in figure 7.1 causes the red LED to light up. And then you just didn't say anything. So, explain how the, how does the question go at this? When the AC signal is less than 4.7 volts, the voltage comparator output goes low, creating a voltage difference to turn on the LED. Oh, wait a second. Oh, it's a pull-up. Oh, crap. Okay. Oh, I didn't see this. Okay. So, I don't have a video on this, but basically, once this part, this may seem a bit unnatural to beginners, but when this part is 0 volts, current will actually flow like this. Current will actually flow like this, and the LED will turn on. So if you will, this is kind of like an inverter. So what you have to explain here is, okay, what you have to note is that, oh, this is being pulled up. Oh, when this is 0, this will actually be turned on. When this is 1, this will actually be turned off. And when this is 1, when this is 8 volts, it current cannot flow. Okay, there's a lot of marking here, so yeah, when this is 8 volts, the current cannot flow. It doesn't work. It doesn't work. Okay. So you have to state, you have to mention that, and in this case, in this case they do lah. So they stated when the AC signal is less than 4.7, they stated the cause, then they stated the process, then they stated the effect. Okay. Section B. Okay, so let's tally up your marks. So, I don't know if this is true. I'm just gonna follow it. Okay. So, 1 plus 1 plus 1 plus 1 plus, oh crap, man, 1 plus 1 plus 1 plus 1 plus 3 plus 2 plus 2 plus 2 plus 1 plus 1 plus 1 plus 3, the 23. That's not that good. Okay, to be fair, a lot of things were not are not in syllabus. You know what? I gotta make a video on this one day. Okay, a lot of things were not in syllabus, and there are a lot of explain questions, which really tests your knowledge. So Yeah. My opinion is for the O levels, right? You will get maybe like half the intensity of this. That's my feeling. Yeah. And there's a lot of analog stuff tested here. I don't think they're gonna test into O levels. If they do, right, everyone is gone already. Everyone will be gone except me. I think. Okay. Anyway, let's move on to section B. So, the maximum resistance of R2 is 10 kilo ohms. Determine the maximum and minimum current. Oh, okay. So basically, right, yeah, I is equals to VR. V is constant, R is changing, and with a variable resistor or a potentiometer here, right, the range would be from 0 ohms all the way to 10 kilo ohms. And now they're asking for maximum and minimum current, right? So just do this twice, set the resistance to 0, and then the effective resistance will be 2.2 kilo ohms plus 0 ohms. Set this resistance to 10 kilo ohms, which is the max, then get the effective resistance again. Do all that shenanigans, and then you will get your answer lah. So 5.5 milliamps, 0. Yeah, you're right lah. Determine the maximum power dissipated across R1. So again, it's just using equations. We know that the equation is P equals V squared over R for power. Plug in the values and then you should get it lah. Don't forget to convert your prefixes, and this is right, yes. Circle the suitable power rating for R1. And then you circle 0.25 watts. Oh yeah, 65.4 milliwatts. That is not watts. It's equals to 123 0.0654. So it has to be 0.25. Yeah, okay, because these are in watts, right? So what I'm doing is I'm converting the milliwatts of the power dissipated across R1 to watts. And then now I get 0.0654. Then what I'm looking for is a value that is higher than 0.0654. And in this case it happens to be this. But I don't need to be too high because it's like wearing tungsten plated armor to a nerf battle lah. It's unnecessary. So 0.25 watts should be the answer lah. And it is. And a reason, okay. It is a higher rating than the calculated value, okay. And it should be at least twice the value of the calculated value. Power rating should be twice the max. I didn't even know that, bro. Power rating should be twice the maximum power, equals 0.132 watts. Hence the next high 0.132. Oh, okay. Okay, what I would have preferred, I'm gonna mark you right, but what I would have preferred in your answer is oh my gosh, is if you showed me actual values. That means, it is higher rated than calculated value, the calculated value being 0.0654 watts, and it is at least two times the value of the calculated value, twice the calculated value being 0.12 or whatever. I would have preferred that. But I'm not marking you wrong, you're actually right. Your reasons are correct. R2 in figure 8.1 is replaced by thermistor, and then they give us the graph. The thermistor is placed in pure melting ice and then subsequently in steam. Figure 8.2 shows the resistance of the thermistor in the following conditions. Oh my gosh. Okay, and then state. So we just look at the graph. So you should be right. State the type of thermistor used in part B. NTC. I would have preferred you to spell out negative temperature coefficient thermistor, but I think NTC is fine. Okay, NTC thermistor as the graph is decreasing in resistance. No. You get 1 mark. You have to state that they have that temperature and resistance has a negative relationship, where when temperature increases, resistance decreases. You have to state that. Yes, you have to state that. So you don't get the full mark here. Using 8.2, compare how the resistance of the thermistor varies with temperature when temperature is between 0 to 50 and 50 to 100 degrees. I don't understand this question at all. What? Compare how it varies. Oh, the rate at which it decreases. So from 0 to 50, 0 to 50, the resistance drops from 600 all the way to 100. That's a 500 ohm drop. But then from 50 to 100, the resistance drops about, that's a straight ass line, man. It drops to about it drops by like 75 only. So the answer is from 0 degrees to 50 degrees, the resistance drops much more significantly than from 50 degrees to 100 degrees, and then you can quote values if you want. Yeah, yes. Determine the change of voltage across the thermistor when it is placed in melting ice and subsequently in steam. So the change of voltage, so what you need to do is V equals IR, right? Do we know the current? Oh, we know resistance, but do we know the current? They're asking for voltage, yeah. So V equals IR. So the only way we know voltage is with current. Okay, basically, you find the voltage when it is in ice, you find the voltage when it is in steam, you take the higher value minus the smaller value, that's a voltage change. Resistance at 0 is 550. Voltage across the thermistor. Oh, they're finding the current. Oh, yeah, okay, so we are referencing this. I was like, my doubt was whether we were referencing this. That's why I didn't know the current. Basically, you can manually find the current because you know that current is equals to voltage divided by resistance, right? We would know the resistance of R2 with the thermistor. So then you just take the main voltage is 12 divided by effective resistance. Effective resistance in a series circuit is the resistance of the resistors just added up together. Do that for when in ice, do that for when in steam, minus the voltages together. From this to that. What? Oh, okay, yeah. No, I thought it was like the answer was 2.3 to 2.5, but never mind. Yeah. Anyway, okay. Super capacitor bank, tough lah. Bro, this is such an old-fashioned system of. Oh my gosh, bro. That's so bad. Okay, anyway. Okay. 9.1 shows photovoltaics system that converts sunlight into electricity using a solar panel. PV system includes a supercapacitor bank to store the electrical energy and a regulator circuit. If you guys did not know, this is obviously the capacitor, but this is the regulation circuit. Fall voltage of the diode is 0.7 volts. When the capacitor bank is fully charged, the voltage at point A, 4.9 volts, determine the potential difference across the solar panel. 4.9 plus 0.7 plus 0.7 plus 0.7 is 7 volts. I think that works. Yeah, okay. Yeah, that works. State the two purposes of these diodes in the circuit to ensure that current flows easily in one direction. That you can't say this. You have to say to ensure that current only flows in the positive direction or only flows in one direction. You cannot say oh flows easily in only one direction. So I'm just stupid lah. You only said one point though. So yeah, the other reason is because these diodes, right, they actually eat up the voltage. So their purpose is to regulate and decrease the voltage inputted inputted to the supercapacitor bank and the supercapacitor bank. So yeah, the supercapacitor bank has an equivalent capacitance of 4.5 farads. It's made up of 4.5 farads, damn, and it's made up of three capacitors connected in a circuit. Figure 9.2 shows three different configurations. If each capacitor is 3 farads, state which. Okay, for a second I was like, nothing is being done. State and verify if the load different. Okay, wait. What is. If each capacitor is 3 farads, yeah, which is used in the supercapacitor bank, show your workings. So what I would do is just get the effective resistance, capacitance of each capacitor bank. Just remember the golden rule. Parallel to get effective capacitance is equals to just this plus this. But in series like here, you actually need to do this. You get the effective capacitance, the capacitance of one, the capacitance of the other, everything to the power of minus one. That's it. You do that for all three, and then you just pick the one that is closest to 4.5 volts. Farads, 4.5 farads. When the capacitor bank is fully charged, determine the amount of charge. Okay, so the equation for that is C equals QV, I think. Q equals VC. Yes, I'm right. Okay, so charge is Q. Then you just plop in the values using this equation. And then 22. Okay. 9.3 shows the voltage regulation circuit and uses a Zener diode with 3.3 volts breakdown voltage. Load resistance varies from 390 ohms to 1.2 kilo ohms. State when when the load resistance is 390, state and verify if the load potential difference is regulated. Okay, what does this mean? Basically, right, I have a video on Zener diodes, but the point of a Zener diode, and this is in reverse bias, what it does is if the voltage across it is higher than its breakdown voltage, which is 3.3 volts, then it will clamp the voltage across it to 3.3 volts. And when it does this clamping, it regulates the voltage. So what they're asking, in other words, is when it's 390, is the voltage higher than 3.3 volts? Because if so, the voltage will be regulated. So what you can do is just V equals I over R. Yeah, V equals I over R, but you don't know I. 390 divided by 390 plus 470. The load. Oh, the load. Oh, I was looking at something else. When the load resistance is 390. Oh, you need to use the current divider circuit equation. You need to use the current. That's crazy. Okay, so yeah, you need to use the current divider equation to find out the current here. So the current. Okay, I'll just talk about it briefly here because I don't have a video on this. Okay, but what it states is that okay, this is basically what we have here. The current divider. Do we need voltage for this? No, right? It's just ratios. No, this is a voltage divider. Wait. Am I dumb? This is just a voltage divider circuit. Am I gone? Yeah, I'm gone. Okay. Yeah. It's just voltage divider, so I'm not gonna talk about it. So you just find if that voltage after using a voltage divider circuit is higher than 3.3 volts, and if it is, which it is not, it's not lah. So in this case, no voltage is regulated. State the amount of current passing through the Zener diode. So we know the voltage and the resistance are. Oh, there's no current passing through the Zener diode. I have no idea why that is true. I'm just gonna skip it for now. I will be skipping it and not returning to it. I have no idea why. I'll just be honest. I have no idea. When the load is 1.2 kilo ohms, determine the amount of current Is that passes through R1. When the load is that. I guess we can find the how you do it. It is voltage divider circuit again. So we get the voltage. Am I looking at the wrong thing? No. It'll be reverse bias. So, oh, okay. But then what? Oh, crap. Yeah, it is for, okay. So basically, right, there's something you need to know. 470 ohms, right? Just imagine it as the resistance of this. Just for of a Zener, just imagine that. Okay, so what they're doing is they're finding the voltage uh, that will be across the Zener diode due to the load, which is voltage divider circuit lah. They find that and then they realize, hey, the voltage is actually higher than 3.3 volts. Wait a minute, won't the Zener diode clamp this down to 3.3 volts? Yes. So therefore, the voltage at here is no longer that high one. Now it's just 3.3 volts. Then we know that this is the resistance, right? V equals IR, that's it, blah 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 blah. Very easy. 9.4 shows that the Zener diode is being inverted. The wording is terrible. State and explain what happens to the PD across the load. When for 390, oh okay. For 390, okay, the facts we need to know is, does it when it was in not inverted lah, when it was not inverted, would the Zener diode have regulated the voltage at 390 ohms? Would it have regulated the voltage at 1.2 kilo ohms? For this, no. For this, yes. The moment you put it in forward bias, it stops regulating the voltage. So it doesn't care whether the voltage across it is higher than 3.3 volts. It's just gonna act like a normal diode. So when the resistance is 390 ohms, the PD across the load will remain the same, or will be, yeah, it will be the same, but when it's 1.2 kilo ohms, it'll be higher. How do they? The load will not be regulated. The voltage across the load is almost zero. Huh? Despite the load condition, the PD will stay 0.7 volts. When the voltage increases above 0.7, am I reading the right thing? I am, what the heck? The Zener diode will be forward biased. That doesn't, I don't know. Yeah, I don't agree with the answer key, I don't know. Yeah. Okay. Alright. Wait, let me read the question again. Explain what happens to the PD across the load. The load. And then like there's no question here lah. Oh, there is. Wait. A scenario that can be described in logic terms is given below. To unlock the door to the computer room that needs two keys. A software engineer and a department manager each hold an identical key. security officer has a different key. To unlock the door, the security officer, so okay, the security officer and either the software engineer or the department manager. So security officer is a must, but E and D either or can, but at least one of them. So yeah, this is right. Complete truth table, this is right. Write down the Boolean expression of X. Okay, so Boolean expression, oh, I have a video on Boolean expression if you want further explanation, but I'll just give you a brief one. Look at the one in the output, write the Boolean expression from this. It will be S times E times D for the variable that in this specific case is 0, add a bar on top. So this would be right if he did that lah, which he has. Yes. Okay, complete the K-map in here from the information on top there. So again, what you do is you write down the ones first, and then it's just like Cartesian coordinate system. You just have to follow. Oh, in this case, 1 0 1. Oh, I look. Oh, 1. Oh, 0. Oh, 1. Oh, 1. You do that for everything else, for the ones. Then you fill the rest with 0. State the simplified Boolean output expression of the K-map. They just do a grouping. I'm not gonna explain grouping. Just watch the video. Yeah, this is right. What the heck? Yeah, this is right. SDSE. This is just factorized. I would accept this. Using logic gates with two inputs, draw on figure 10.1 the logic circuit that would implement the simplified Boolean expression. So, the method for this is, okay, just know times when two variables are multiplied together is AND, when two variables are added together is OR, and when there's a bar is NOT. So, we look at the first expression that is ANDed together, then we draw an AND gate. Oh, ST are ANDed together. Oh. Then we look at the next one. Oh, SE and S and E are ANDed together. Oh. Oh, they are ORed together. Oh. Okay. The logic output X is fed into a circuit that consists of the components shown in the table. Two resistors, green LED, red LED, a relay. Table 10.3 shows the... Oh, when the output X is 1, the relay coil is energized. The green LED is turned on and the door is unlocked. Complete the circuit on 10.2 to show how it works. Hey, why did you do, why did you do nothing? Like 50% of section B is like not done. Okay, anyway. Okay, complete the circuit on 10.2 to show how it works. Logic output X, okay. I'm gonna, okay, yeah, it's probably just like this. Okay, is it, oh, normally, oh, whoa, what am I doing? Okay, it says when the coil is energized, the green LED is turned on, and then it doesn't talk about the red LED. But what I'm guessing, is that when the green LED is off, the red LED is on. That's what I'm guessing. That's probably true, because yeah. So okay, two resistors, two LEDs. Bro, this sucks on ice. So this is the red LED, this is the green LED. Yeah. Yeah. Okay. Name the type of electromechanical relay used. SPDT. Yep. Single pole dual throw. 11.1 shows a part of a LDR sensor circuit using a BJT. Okay. Oh, 1 mega ohm, alright. Name the type of transistor. The arrow is going out, so it should be NPN, yeah. If it's going in, right, to this bar, then it is PNP. The buzzer is a polarized component. State what is meant by polarized. Polarized means the component has two terminals, positive and negative. Nope. Polarized means that current can only flow through one way. If you go through the other way, it will damage the component. What? I'm not giving you... Okay, I'm gonna give you the mark. But you... Are you serious? Okay, my computer's hanging. I would add the point I mentioned. State the light condition, either bright or dark, that will turn on the buzzer. Oh, so for this you need to know you need to know about your LDR. It needs to be in bright light condition. This is because the resistor is a LDR, which will require light for it to lose resistance. Hence, the LDR resistance decreases, and the circuit would be operated as the resistance. The circuit will be operated as the resistance is suitable enough for current to flow through the circuit. You get like that's like almost there. In bright light, okay, yeah. So yes, the LDR resistance will decrease. Yes, the PD across X would increase. So I would state from here. I would state, oh, because it's a voltage divider, using the voltage divider equation, as resistance, as the LDR resistance decreases, the voltage at X will actually increase. So for this, you get 2 marks. Not too shabby. Transistor VCE is 0.2. Calculate the voltage across the buzzer when it's fully saturated. Okay, VCE 0.2 volts. We've talked about this in section A. So this is just KVL again. Cause 8 volts, the buzzer. Then VCE, yeah, which is 0.2, and then ground. That's it. So, this voltage by this voltage equals 8. Oh my gosh, basic algebra, 1 unknown. That's it. 7.8. To drive the buzzer in part B, the collector current is 0.15 amps, and then the base current is 750 microamps. Calculate the current gain. Current gain is IC over IB, so you just plug in the values. Okay. Select a transistor from this table that would be suitable for that. Maximum IC, the current gain. Okay, yeah. You just look at the values. Oh, this is closest. Oh, this is closest. That's it. That's all you have to do. State a reason for your choice of transistor. It is closest to the calculated gain. Yeah, I think that works. Yeah, yeah. I would have preferred if you said current gain or DC current gain. Alright, let's move on. Transistor in this saturates with a base voltage of VBE 0.7 volts. Voltage at X is 4.9 volts. Okay. Using the transistor selected in DI, calculate the resistance. So VBE is 0.7 volts because just fun fact, this is a diode, or not fun fact, you need to know. It's a diode. This here we have the voltage, and then we know the current here. So this is just a this is just a simplified 0.7 volts here, then 4.9 here, and we know the current Oh, and this is the collector, so 0.15 amps. So we have voltage, we have current, therefore we can find resistance because R is V over I. 6.16. Yeah. Circle the most suitable resistor. Ooh, I don't think that's right. Oh, okay. I was gonna pick this because like protection, but in this case, right, in this specific context, you want the resistor that is lowest and closest. Lowest because, right, the lower your resistance, the higher your current, and then the more saturated your transistor becomes. And you want it to be saturated. So you get 1 mark because you need to state that, oh, and a lower resistance from the actual calculated resistance will provide a higher saturation level for the transistor. So yes, state one modification to amplify. Amplify means even amplify the current even further. Darlington pair, correct. That's it. Alright. Time to tally the marks. Okay, for this one, it doesn't look too good, friend. Um, okay, so 2 plus 2 plus 2 did I yep, plus 1 plus 1 plus 1 plus 1 plus 1 whole 9 plus 3 plus 2 plus 2 plus 3 plus 1 plus 1 plus 1 plus 2 plus 1 plus 1 plus 1 plus 1 plus 3 plus 1 plus 1. 35 out of 60 or out of 57. Oh, that's terrible, man. I'm so sorry. Okay, so that would be 58 out of 95, which lands you 61%. Hey, not bad. Alright, so yeah. I mean, take this paper not really with a grain of salt. There are still quite important learning points from here. But yeah, a lot of the stuff in here was our syllabus. Um I don't really have anything else to say. Alright, yeah, I'm done.